Hello, this is mathjazz from Almost Cool. This is the first video in our series of videos of common optimization problems. Today, we're going to optimize two rectangular fields that share a common fence. The problem statement is, suppose that you have material to make 1,000 feet of fence, and you want to make the largest pair of rectangular enclosed areas, as in the diagram below, possible with the 1,000 feet of fence. What is the area and what are the dimensions of such a structure? Here's the diagram. So, the first thing that we're going to have to do with this diagram is we're going to have to label the sides of these fields. I chose to label the horizontal side X and the vertical side Y. I realize this is a top-down view of a field, so the fence Y is actually not going vertically. But on the screen, Y will be the vertical sides of these fields, and X will be the horizontal side of these fields. Once we've done that, we need to make an equation that relates the area of the field to the 1,000 feet of fence that we have. So the first thing that we're going to do is we're going to realize that the sum of the lengths of the sides of the fields must add up to 1,000 feet. This gives us that 2x plus 3y equals 1,000. Further, we also realize that the area of these two fields is x times y. If we solve for y and substitute into the first equation, we get that the area of the field is equal to negative 2x squared over 3 plus 1,000x over 3. To maximize the area, we need to find the roots of the derivative of the area equation. So we take the derivative and get a prime of x equals negative 4x over 3 plus 1,000 over 3. And then we set the derivative equal to 0. After we do this, we find that the critical point is 250. We get that from subtracting 4x over 3 from both sides, multiplying both sides by 3, and then dividing by 4. Now, we have to use the second derivative test to see if this is a maximum or a minimum. Now, it's going to end up that this is a maximum because we were asked to find a maximum area. But since a is a polynomial, and so it's continuous and differentiable everywhere, knowing that the second derivative is the constant function, the constant negative function, negative 4 over 3, tells us that x at 250 is a global maximizer for this equation. That is, if a weren't a continuous differentiable function, knowing that the second derivative is constant and negative doesn't necessarily give us that we have a global maximum. But if a function is continuous, differentiable, and has a negative second derivative everywhere, then we know that any critical point must be a global maximum. So, now that we know that x gives us the maximum area, we can plug 250 into our area equation and get that the area is 125,000 over 3. And we can plug x into, when we solved for y earlier from the perimeter equation, if we plug 250 in for x in that equation, we find that y must be 500 over 3. So that gives us dimensions of 250, 500 over 3 as the x and y dimensions of that those two fields together. And we know that the area is 125,000 over 3. Thank you for watching this video. Contact information is on the screen and in the description of the video down below. I hope that you're enjoying learning calculus, and I hope that you have a great day. Goodbye.